Okay, so we'll start this post-grad session, and we're happy to have Jyotirmoy from IIT Kanpur, and he will talk about thermal product formula for shear bolts.
All right. Yeah. So let me begin by thanking the organizers of this beautiful workshop. Like all the string theory group here, I guess, is involved, and particularly Apratim and Deepta, who is not here. So thanks a lot for organizing such a nice workshop and inviting me here. And before I begin, let me make two comments. There are two connections with IIT Kanpur and this work that I'm going to talk about. Some of the things that I'm going to say, I think, we started with, I was discussing with Niloy like 10 years back, it went into a cold storage, so nothing got done. And so some of those things, got revived in this work. And also, I think last time I came to IIT Kanpur was about like 2-3 years ago, where I had missed one very interesting paper that came out on the archive, and it was brought to my notice, when I was visiting IIT Kanpur at that time. And this work is kind of a result of trying to understand that paper slightly better. Okay, so this is very very nice that I'm talking about it here. So this work was done along with three of the students at IIT Kanpur, Nivedita, Aditya, and Shorav. And again, as I was trying to say, this kind of very strongly borrows from a work by Matthew Doralson, Sasha Zvodov, and I think there are two other authors, Loso and I think Carlson. There were two other authors, 4 authors. So that draws very and the title of the paper was Thermal Product Formula. And we try to, and there were some questions, while trying to understand that, we're trying to answer some questions, which I will try to describe. And so this basically, this name kind of also, is very similar, but we look at a slightly different scenario, which were not considered by them. And I in some sense, slightly generalize their statement. So what is this about? So this is about thermal 2-point correlation functions in CFTs with, where particularly, we are going to use holographic tubes, okay, to understand the structure of thermal 2-point correlation functions in CFTs. And of course, to this audience, I don't have to emphasize the importance of thermal 2-point functions. I mean, they have very important, applications in terms of, let's say, thermalization process and in particular transport properties. So all these are encoded in these thermal 2-point functions, which and we want to understand the thermal 2-point function and their structure in slightly more detailed, particularly using holographic tools. Okay, so that's the main setting. So in case of when I talk about thermal states in holography, the dominant contribution is coming from a black hole, which is there in the ADS bulk. And so much of what I'm going to talk about is basically black hole or black brane physics that I'm going to describe here. So so again, these black holes are characterized by something known as quasi-normal modes. For those who, I'm sure all of you have heard this terminology, but I will also describe a little bit of what I mean. These are essentially the linearized fluctuation spectrum around a given solution of Einstein's equation. The black hole is a solution of Einstein's equation, and the quasi-normal modes are linearized fluctuation spectrum around a particular black hole solution. Okay, so and there is an intimate connection of these so-called quasi-normal modes. Yeah, sure. Change. This is not right. Not a fast forward. Is this okay for you? Yeah. You're not the sort will jump around, right? So this is a more stable thing. Places. You practice mathematics. Oh, it's directly playing from the USB. I think that's the problem. So let me just.
And this is something that's,
Why is this not clean up?
oh, it's happening here.
Maybe then even my old laptop would work.
Just hold on a second. I'll put this in now.
That looks good.
No, it doesn't look good.
Okay, then it was not my laptop. Okay.
This plug is, I mean, this socket is not great actually. Right. No, it's not the laptop, it's the wire here. Yeah, okay, let's sort of fix this. Huh? Yeah, I guess we have to do it. That was not happening yesterday, right? Let me try and see if they have another.
Okay, yeah, so I'll be talking about this thermal 2-point function, this holographic thermal 2-point functions, and so again, the primary objective is to understand the role played by the QNMs. Yeah.
It's still bigger, so.
Yeah, it's still because. Yeah, so what is the role of these QNMs in determining these 2-point functions? As you will see that it determines these 2-point functions almost completely. That's kind of the bottom line, but in a very interesting way. So that's what we are going to talk about. And so here, there are various topics. I will try to cover. So I'll start with a basic introduction of this work that I was talking about. This primary reference, this Dodelson et al.'s work, and yeah.
It's a nonsense work. It's something that they don't. The computer doesn't like. Yeah. Okay. You're the one with the fancy stuff today.
Okay. Okay. All right.
Well, if something doesn't work, something else. Yeah, let me move that outfit.
Ah.
Because that is just, yeah. You go on with your program.
All right. So okay, so there are two systems that I will talk about today, where I'm going to use them to experimentally verify, the conjecture about this so-called thermal product formula. And the first system is going to be a charged black hole, okay, a charged black brane in ADS5. Okay, so this has the usual, n equal to 4 Yang-Mills, which is the dual. And then I'm going to, introduce so this one is from the boundary point of view, it describes a CFT with a conserved global U1 charge. Okay, so that's the setting where, I want to test this kind of hypothesis. And so now that in the next part, I'll modify that by introducing a Chern-Simons term in the bulk, where this U1 will be a anomalous U1. Okay, and this is also there is also a truncation of n equal to 4 Yang-Mills, where such Chern-Simons terms are present. And so I'll describe it in more detail, while we go on, and then I will, conclude with some outlook. I think there are some interesting. Oh, okay, it's right. Yeah. Okay. Okay. So all right. So now, so before we start, let me tell you, so there are some terminology that I'm going to use while while presenting the results. So basically, we are going to talk about thermal 2-point functions, right? So so there are various varieties in which this thermal 2-point functions can be expressed. Of course, we are familiar with this retarded correlator. This is the field theory formula for the thermal correlator. And so there is another version without the commutator, and this is known as the Whiteman function. Okay. And if we take this Whiteman function and analytically continue it into put a imaginary part to time, then this is known as the two-sided Whiteman correlator. Okay, and this one is the object which why is it called two-sided? It has like a this word has an origin in holographic systems only, because in this case you can think of the situation where there are two decoupled CFTs in this black hole geometry, and it is a correlator where one leg is on one side of the CFT and the other leg is on the other side. So this is like a it's just a simple analytic continuation of the Whiteman function. This is the two-sided Whiteman correlator, and this will be our main interest. Okay, this object is going to be our main interest. So, and if we just do a Fourier transform, this, as you can see, if we just do a Fourier transform, the two-sided correlator, the two-sided Whiteman function can be expressed in this way, and then you can also express this object in terms of the imaginary part of the retarded correlator divided by this Sinch factor. Okay, this Sinch factor is kind of important in getting the kind of match that we are going to talk about. Okay, so this object is somehow very important, and this is so any of the so let's say if we know this object, this two-sided Whiteman function, then I know the imaginary part of the retarded correlator and vice versa. And if I know the imaginary part, I can of course know the real part, by something like Kramer's conic, and then I know the whole correlator. Okay, so I have so this is the most simplest object which has the most simplest formula. Okay, so this is the function that we are going to talk about. Okay, so this two-sided Whiteman correlator is the one that we are going to talk about. This is the formula that we should remember. Good. Now, so the claim in this paper, this is our main reference that I was talking about. The claim in this paper is that in holographic theories, this two-sided Whiteman function is entirely given by the black hole quasi-normal modes. Okay, so here omega n are the black hole quasi-normal modes. Okay, yes.
Theories for 2D CFTs, you mean that C is much greater than 1? Some theories are...
So it's large n. Yes, you are right. Okay, so that's very important for this formula to hold. So if that's very important. This is something I would have emphasized later on. But this is very important for this formula to hold, because as you will see, I will sketch a proof which they have given in their paper. For that, there are some analytic properties that you have to assume, and that is not true even like, if you have 1/n corrections, those properties, doesn't really hold. So I'll try to point them out. And but this is the main result. Okay, it's a simple formula, yes. No, let me, very good question. Okay, good. Okay, so the point is that, this denominator, okay, the fact, what is the surprise here? So of course, let me, before answering that, let me mention one small thing. I have only expressed omegas here, but time, but there's also a space coordinate. We can take a Fourier transform of that. So the so everything here, also depends on k, can depend on k, but I've just expressed the omega dependence, right? So if you so for instance, these so-called quasi-normal modes, they are going to be omega, also can be a function of k. Okay, if you have the spectral momentum. So now to answer your question, it has been I think from the beginning of ADSA, anybody who is slightly familiar would know that the quasi-normal modes form the poles of the 2-point function. Okay, like that is what Steiner and so on had. What is the surprising bit here is that this is all there is. The numerator. In the numerator, there's just one, there's no omega dependence in the numerator. Okay, that is the surprising bit. That, if the whole function, dependence of omega on the whole function is captured just by these poles. That is a very big thing. Okay, because,
What is the meaning of this statement for specific operators?
So that is what the point is about. So these, this thing was, demonstrated for a certain class of operators in this paper, and we are going to look at a different class of operators and try to see whether this also holds. And we'll see that so there were some puzzles also which were presented in this paper. So yeah, I will talk about the class of operators that's there. Okay. The operator information is in G naught and this WNs. Yeah, right. Yeah. So yes. Yes.
I mean, they are, of course, there was one more connection. So they also had what similar kind of that of course it is correct. There also you have the same situation that the poles appear.
The poles are always there. That I'm not contesting. Okay, the pole, it is very, common knowledge that the poles will be determined by the quasi-normal modes. Okay, but what about the numerator? What is the omega dependence of the numerator? That's the question. And these guys, nail that question, I believe. Okay, and that makes it very interesting. They say there is no omega dependence in the numerator. Okay, it's, this guy is just a function of k. This G naught, this is a constant, is just a function of k. That's it. There's no omega dependence in the numerator. So, that I think is the powerful content of the statement. Okay, and as you will see that we are going to claim that, this depends on the choice of operator. This statement depends on the choice of operator. If you choose certain operators which kind of mix with other operators, in a certain sense I'll describe, okay, they have non-trivial correlation functions with other kind of operators, okay. Particularly, we are going to look at conserved currents in this theory. So in that case, what happens is this slightly generalizes what we found, okay, in a very non-trivial way. The arguments, become very non-trivial, and it becomes, product, sum of products. Instead of just a single product, it becomes sum of products, okay, where, this G naught and this omega n, all of these are functions of k. But as you see now, the numerator is not trivial like earlier, okay, because now there are non-trivial zeros, which you can figure out given the information of this G naught. Okay, because there are two terms now, right? So this kind of structure, I think, holds in general, and I will have a very, a rough argument which will tell you, perhaps this structure holds very generally. This slightly generalized structure holds very generally. Okay, that's going to be one of the main points of what I'm going to talk about. Okay, so okay, let's continue and we'll. So I will explain that point also. The point is, at this point, so let's try to, answer that question immediately. So, so we are doing a holographic calculation, right? So what these guys had was a proof that if you, for instance, looked at scalar fluctuations about a certain black hole that corresponded to some scalar operator from the boundary point of view. So this is like some scalar primary, from the CFT language. So in that case, they have a proof, holographic proof, that this is valid, without any sum. Okay. Now, and they said that, well, if we now consider, for instance, the stress tensor correlator, they experimentally observed that it was true, the formula was valid, but they said, our proof don't apply for that. Okay. So, there needs to be a new proof. So now what we did was we looked at a scenario where, the stress tensor was also involved and there was a conserved global current also. Okay, so there were non-trivial correlation functions between the stress tensor and the global current. And as I will try to tell you, that setting helped us answer their question that, why it was working for the stress tensor as well. Okay, that's the point. Okay, so so that is the idea. And while doing that, we realized that this is a more general form, which is perhaps valid not only for holographic theory, but probably it's a large N. If you take large N theory, I think they also mention it, and one of their authors, have several papers after that, where they looked at systems like for instance, SYK at large N but finite coupling, like that. And they were saying that in all those theories, this structure kind of holds, even for non-holographic case where there's no immediate holographic dual. This kind of structure holds. Okay.
So if this holds for the stress tensor and currents, why? I mean, shouldn't there be spin dependence in what tensor structures?
Let me, give me, let me show you it is there. let me present you the results. I've written it in a way that also, so how should I say? Yeah, you are right. And the spin dependence, if you like, is carried by this G naught here. Okay, and yeah, but so the way I have made this generalization kind of looks at a particular sector. Okay, so we are looking. I think it will be answered better when I have those formulas on board. Okay, yes, definitely there is a spin dependence, and the spin dependence, if you like, is captured by this G naught here. Okay, and also it depends on which this equivalence depends on which operator you are looking at. So the K dependence as well as the spin dependence of the operator, that content, these two objects are function of the operator, of various, the dimension of the operator and the spin of the operator, this equivalence and this G naught is sensitive to that. Okay, that's the statement. Okay, yeah.
Probably from the point of view of the equivalent calculation and the kind of question that Kaushik was asking. And if you just trying to look at the linearized perturbation.
Yes.
It's important which sector you turn on.
It's important which sector you turn on, and that is the shear sector. Yeah.
Then to turn on, let's say the vector perturbation.
Right.
The tensor perturbation.
Yeah.
The phase of the tensor perturbation may mix with the scalar. Depends on the symmetry which.
Correct.
That might
Correct.
be another way of saying.
Yeah. So, but I think here the question was, for instance, you are looking at an operator, that for instance, the current operator, that will have like a j equal to 1, right? Where does that j go? So that information that we are looking at current correlations, that goes into this QNMs, and as you will see the process, and this G naught, that's the point. Okay, good. So again, so we are going to consider R-charged black holes in ADS5 again, which is a particular consistent truncation of type 2b supergravity. And so here, so this is where I'm reviewing a little bit of the proof is slightly complicated to present in full glory, but I will try to highlight the main points of the proof that this reference had. Okay, so they had presented a proof for this scalar fluctuations. So what I have here is a metric of a black brane. Okay, so we are going to look at a charged black brane, but their proof that they have given is presented for a uncharged black brane solution that you have for the Einstein's equation, and you consider a scalar fluctuation on top of that, with a mass m. And so by that, what I mean is like, you consider phi, of course, this is a linear equation. You don't have to linearize it, but this is, I omega t and IKS kind of fluctuations. And you take that and plug it back into this equation, then you will get a equation which is of this form. Okay. So here I have used, of course, there's here R is or Z is the radial coordinate. And it's easy to write down this equation in the radial coordinate, but that's a little more complicated. But if you use the so-called tortoise coordinates, you use the corresponding tortoise coordinates. This equation resembles that of a one-dimensional Schrodinger equation, as you can see, with some potential, which is kind of dependent on the problem. Okay, dependent on the background. In this case, it's a Schwarzschild black hole background. And so there are two things that you can do with this equation. Okay, this is a solution. So this is the equation that you get by considering scalar fluctuations on top of this black hole geometry. And there are two things that you can do. You can compute the thermal, retarded 2-point function of the operator dual to the phi field from the boundary perspective. Okay, that you can do. And there is a standard ADS-CFT dictionary which allows you to do that. And you can also compute the quasi-normal modes from the same equation. Okay, you just need to use two different boundary conditions. Okay, so you solve this equation with an ingoing boundary condition at the horizon. Okay, and a so-called normalizable condition at the boundary. Okay, that will give you the spectrum of quasi-normal modes for this particular kind of fluctuation. Okay, so you are going to use this equation to find the values of those modes. Okay, and secondly, what you can do is, if you look at the asymptotic behavior of this phi field near the boundary, you will have two kinds of falloffs. Okay, and anybody who is familiar with standard ADS-CFT would know that, one of these things is interpreted as the operator expectation value and the other is the source. Okay. So if you now take this and put it into your, Einstein's equation, and so you will have a functional, which is, so you will have a function of these sources. Okay. This is, so from the boundary point of view, you take this on-shell action, and if you differentiate with respect to the sources, you'll get the 2-point function. Okay. So physically speaking, that also you just, analyze this equation, and, you put in normalizable boundary conditions at the horizon, but at the boundary, now you don't put, you put in ingoing boundary condition at the horizon, but at the boundary, you calculate, you keep both the sources, okay, and the operator, and then the corresponding ratio, fixes the 2-point function. This comes out of this ADS-CFT dictionary of, finding the on-shell action and, varying it with respect to the source twice and setting the source to 0. That's the procedure which gives you this. But, practically speaking, this is the formal thing that you have to do. Solve this equation and find these two numbers and take the ratio. Okay, that's the thing that you need to do. So you see, this one equation, from this one equation, you are able to find the retarded correlator, okay, from this one equation, and the same equation also gives you the values of the QNMs, just by doing a slightly different kind of analysis. Okay, so yeah, so basically, again, for people who haven't, the QNMs, so you put two different kind of boundary, like ingoing at the boundary and normalizable at the ingoing at the horizon and normalizable at the boundary. If you put that boundary, then you ask, what is the value of omega for which I can find a solution? Okay, and those are usually discrete values of omega. Those are the QNMs in our problem. So that's the setting. Now, once we have these two information coming out of this equation, you can show that. Okay. So once this happens, so as you can very roughly imagine, wherever the sources are going to go to 0, that means it becomes normalizable. There will be a pole of this retarded correlator. That kind of that's kind of obvious from this statement only. Okay, the way I have written it. So yeah.
In the dual perspective, the CFT you have, it's a compacting one circle compactified.
No, there's time as well as there's dynamics at finite temperature. So there's a black hole. So if you hit it, so it's not a thermal equilibrium scenario. It's slightly away from equilibrium, but it's a linearized fluctuation about equilibrium. Okay, so that's the one that the omegas capture. Okay, so it's not thermal equilibrium; it's linearized fluctuations about thermal equilibrium. So in the equilibrium phase, but you compute it by considering linear fluctuations about the that's the point.
The correlator that you consider,
yeah, it's a property of that thermal state. Yeah.
And the correlator that you consider is only for that fluctuations.
Yeah. Right. So now you can look at this function, the 2-point function, the corresponding, so as I said, here you can find the retarded correlator, and with the formula that I showed you in the first slide, you can go ahead and compute the corresponding Whiteman function as a function of omega, you see, because this is a function of omega, okay? And that, so this is a function of omega, but the QNMs are the values of omega for which there is a solution, okay? So there are two different things. So when you find this ratio, you get a function of omega, and that you can put into that formula to find what is the corresponding Whiteman function, right? So you can do that, and so when you do that, you realize that this Whiteman function has these properties. Okay, so the first property is that of meromorphy. Okay, so in this scenario, you will always have isolated simple poles. Okay, wherever these QNMs occur, you will have isolated simple poles. Okay, of course, there are situations, as many of us here is aware of, even in holography, where this assumption breaks down. Okay, and this was one of the points. If you move away from large N, this meromorphic assumption would kind of may break down, okay, if you move away from large N, because there can be like cuts in the 2-point function essentially, okay, if you move away from large N. So now, so as long as this property holds, and as long as this 1 by omega 1 by W, 1 by this two-sided Whiteman is an entire function of order 1. This is just a fancy way of saying that at large values of omega, it's exponential. Okay, that's the idea. So as long as these two properties, these two properties are very generic for holographic theories, frankly. Okay, these two properties almost always, if you are not looking at something like an extremal black hole or something where this property breaks down, these two properties are valid for black holes generically. What is questionable or what is, non-generic is this point about no zeros. Okay, so the point is, if you assume that W has no zeros, okay, if you assume W has no zeros, now you ask, how can I say W has no zeros? So this is something that has to be proved by looking at the equation. Okay, this is the point. These 2 points are generic properties of holographic Whiteman functions, but this one is something that one has to show and prove because it's not clear whether it will have any zero. But if these 3 properties hold, that was the point of their paper. If these 3 properties hold, then okay, so basically, the statement is, the bottom line is that if these 3 properties hold, I'll have a slide later on saying that, if these 3 properties hold, then that thermal product formula kind of follows by, again, a fancy theorem, Hadamard's factorization theorem implies that there will be a, that product formula will, should be valid. Okay, so that's the main point. But what about this no zero condition? Okay, that has to be proved. And that, these authors, go on proving it. And, as I said, this is like a Schrodinger equation. And so what you can show is if this potential that is involved here, okay, has certain kind of behavior, both near the boundary and near the horizon, if it has a specific kind of behavior, as I have mentioned here, okay, and it is like regular, in between, okay, if this potential has this property, then, the regularity in between is very important, okay, the potential has to be regular in between and for all values of omega, okay, only then you can claim, there is a proof, again, slightly involved, which I'm not getting into, that, there won't be any zeros for this, 2-point function computed from the asymptotic fall-off of the phi field. Okay. So what is the main ingredient, therefore? This equation is important. And, if in this equation, the fact that V of U has this kind of property and regular property, that is very important. Okay. Let's keep this in mind for the proof to hold. This is very important. Okay. So, this was pointed out in their paper that, although the formula is valid for, let's say, stress tensor operators, but they show it that it is valid. Look, numerically, we can show that it is valid. Okay, because you can do the 2 computations numerically in some background, and you can show. But they are saying that, okay, this proof is not valid for the corresponding corresponding metric fluctuations. Okay, I will write down the metric fluctuation equation. You'll see there that this argument is not valid. So our proof really doesn't apply, but somehow it's valid. This thing is valid. Okay, so that was one of the points. Okay, so yes, this is 5-dimension and this is standard, like type 2 is supergravity transition. Okay, yeah. It is 4 and it is 5. Sorry, it is 5 and n equal to 4 Young-Mills. Yeah. Okay, so everything that I'm going to say, except one difference I'll point out. How there's it's valid for n equal to 4 Young-Mills. Okay, so okay, so as I said, if you have those 3 conditions and yeah.
So it is not going to be valid if I set up the problem in ADS course.
I think it will be valid. Okay, I think it will be valid, but I mean, whatever we did here is, I think, as I said, it depends on, very crucially, this is very interesting. It depends on these 3 properties. And if these 3 properties holds for any equation, okay, this is, if you like, very generic, as I will try to argue. Okay, the point was that, this no zero condition is also very generic when you think about the problem in a certain sense. That will be my point. Okay, so, here it doesn't seem like that, but it's true. We'll get there, I'll try to explain. Okay, so, good. So once we have those 3 conditions, and we also put in some, statement of the QNMs, following from unitarity and, some property of the correlators following from the KMS conditions, then it follows that this structure of the 2-sided Whiteman function must be valid. Okay. So if I know the QNMs, I just put it into this formula and accept this normalization. I know the omega dependence of the two-sided correlation immediately from the knowledge of the from the knowledge of the QNMs, and I can compute them independently holographically, and I can cross-check whether these two match. So there's a question of matching. Okay. So holographically, it is slightly easier to compute the retarded correlator, and therefore, the relationship between the two-sided correlator and the retarded correlator is kind of significant in seeing the match. Holomorphic function of I think you would need holomorphic dependence on omega because it's an entire function of order 1.
Multiply this right hand side.
Yeah. So right, but so that's the thing. You could. So that's the no. That's the thing. So you could have a multiplication by this function of omega, but there's a theorem which says that this has to factorize into a form like this. So the pole structure is there. So the statement of the theorem is that once you have this pole structure and you have the properties that I mentioned, then the function itself factorizes in this way. So it's a product of these factors.
No, I think the question is, if I assume the 3 properties that you mentioned in the previous
then
slide.
this is the statement of the theorem that it has to be of this form.
No, but he is saying, if I add a FW in the numerator and assume that to be holomorphic, then that will satisfy all the 3 properties that you wrote down.
Order one.
It will not be order 1. Yeah. The asymptotic fall-off will not be order 1. Yeah. Exponential.
But right, so you are assuming
Yeah.
that will
So that goes into the so then you are asking me how to prove Hadamard's factorization theorem. I don't know. Okay. So but there's a theorem. Okay. So yeah. Okay. Okay. But anyway, so this is what it is. Okay. So let's and as we'll see, there's a very good agreement, between the two ways of finding it. When you do numerics. Okay. So that tells us that this works. Yeah.
Maybe not about this. Using this product, the injections, it can to the divergence, and then this omega dependence. So, yeah, anyway,
Yeah, let's discuss this. Of course, it's a very interesting question that what happens in field theories. Okay, so this is like a prototype. As ADS-CFT is a prototype. Okay, it may be valid for certain class of field theories, but that there is no statement about. Okay, at the moment. So, but there are certain field theories, examples which has been tested, and there this structure kind of comes out. Okay, in fact, there's a paper by this. One of these authors that tells us that there is kind of a black hole spectrum in many of these theories. So it kind of comes out. You can obtain what these omega n's are, and you can try to say that these are some kind of QNMs for certain kind like black hole like behavior in field theories that can be observed in this way. Okay, if you have this structure, but there's I don't think any generic statement about the structure of these 2-point functions for generic field theories. Okay, that's not the point here. Anyway, so good. Yeah, so one thing that I want to emphasize is that this follows therefore from a mathematical property of a single differential equation. Okay, so if I take a single differential equation, there are 2 things that I can compute out of it, and they are related in a particular way. So it's a mathematical property of a single differential equation. Okay, so good. Oops. Okay, so now let me generalize the setting and go to the setting that we have looked at. So the first generalization that we do is we consider a Maxwell-Einstein theory. Okay, in the bulk. Again, this is like a consistent. So this this Maxwell field in the boundary corresponds to a U1 global charge, and this U1 is a part of the R symmetry of n equal to 4 Yang-Mills. Okay, so this is a consistent truncation of type 2 supergravity. And there's a solution. This is very well known, like, it's a charged black brane solution. Okay, where so this is a state where you have a from the CFT point of view, this is a state where you have a temperature and a chemical potential, essentially. Okay, there's a uniform temperature and a uniform chemical potential from the boundary CFT point of view. Okay, so in this state, we can go ahead and we can compute linearized fluctuations. Okay, we can try to write down the linearized fluctuation equations. So of course, this is the format that, this G naught is the black brane, and the fluctuations, I'm going to work in linearized. So now these equations are nonlinear, okay, unlike the scalar equation. So I'm going to linearize with respect to this amplitude, and there are, e to the power ikx and I omega t fluctuations which are there. Okay, so we are also keeping k, for instance. Okay, earlier, I haven't emphasized that point, but the spatial momentum is also there. Okay. So once you consider all these fluctuations, you can classify these fluctuations into 3 categories, essentially. Okay, so if I have a k vector, okay, that will break the boundary. So I'm going to, so this is like in the so-called Poincare patch. Okay, so where I have translational invariance, translational and rotational invariance on the boundary. And so the presence of a k vector breaks my rotational invariance SO3 into, there's a remnant SO2 symmetry, okay, because there's a vector. And I can classify these modes that are there based on the SO2 charges. Okay, there are these, plus minus 2, plus minus 1, and 0. Okay, this plus minus 1 is the vector sector, which I'm calling the shear sector. And this is the sector I'm going to emphasize on. Okay, you'll see there's another reason why I'm interested in this sector, except the fact that this is the next simplest after the, let's say, this plus minus 2 sector. Okay, this is the, if it like medium in simplicity. The scalar sector is quite complicated, involves more fields. So this is the sector that I'm going to look at. And what are the fluctuations present in this sector? It's basically certain components of the metric and the gauge field. So again, for people who haven't really seen this before, particularly the students, let me mention what do I mean by sectors. Why am I interested? So if you write down the Einstein's equation and do these fluctuations and linearize it, then you will see that certain equations are coupled and certain equations are certain fluctuations are coupled with each other and certain fluctuations are not coupled with each other. Okay, so depending on which sector these fluctuations live in, they are coupled with each other. Okay, and for instance, a fluctuation from this sector will never couple with a fluctuation from the other sector. Okay, so that's why it is consistent to look at a particular sector and keep all the fluctuations and try to study them. Okay, and so in this sense, this is going back to your question. So you see, when I keep certain kinds of metric fluctuations, only certain components of stress tensor are turned on, because this metric couples to the boundary stress tensor. Okay, so in this sector, I'll be only able to talk about the correlation function of certain components of the energy momentum tensor with the current. So I don't have that full what I call the SO3 symmetry with respect to which I'm going to characterize the spins. That is not there. Okay, in this because there's a k in the game. There's a k vector in the game. Okay, also. Okay, so again, this is the spectrum I'm interested in. And so in this particular sector, the so-called shear sector. So although, as you can see, so here let me make an important point. The fluctuations that are there, I have listed. There are fixed fluctuations. Okay, so it so happens that you will see that this 3 out of the 6, which I'm characterizing by H, F, and B, the equations for this and this are going to be identical in this scenario, and they're going to be decoupled. Okay, so I can truncate these 3 fields as well. Okay, and from the leftover 3 fluctuations that I have, there are only 2 relevant combinations that are gauge invariant. And so essentially, the bottom line is I can take my Maxwell-Einstein's equations, okay, keep only these fluctuations that are there, these three fluctuations, and consider a combination of these three fluctuations when I get two equations for two variables, and these two variables are G and B, essentially. Okay. So I need to solve for this G and B. So this G and B that I have written here are the equivalent of the phi scalar field that I had, talked about before. Okay. So now I have two equations, and these G and B equations are coupled with each other. That's the point. Okay. They're coupled with each other. Okay. And yeah, yes. Yeah.
So if I take this K to 0,
Yes.
then would I just recover SO3?
You'll recover SO3, and then this thing will also simplify. Okay. So then these equations, the equation that we'll see in the next slide, that will also simplify. Setting K to 0 will decouple some of the equations also. Okay. Then so setting K to 0, I think will give you two independent equations for G and B separately. Okay. So the coupling will kind of go away between these two quantities. Okay. So in that case, as you can see here, this F and H, they are the metric fluctuations. Okay. And this B is the gauge field fluctuation. And there's a coupling between the two. Let me show you. So although it's a little bit complicated, but this is an instructive equation. I really want to point out certain things. That's why I put it in. So this is a resultant equation for G and B, where the prime is again with respect to one of the coordinates that remain, the Z coordinate in the bulk. Okay. So right. So what I want to say is, if you set K to 0, as you will see, then you see, the coupling vanishes, and you get, in this particular sector, if you set K to 0, you get the Einstein's equation and the Maxwell's equation separately. Okay, that's what happens. Okay, so good. So yeah, right. So but we have to solve this equation, and so as I was mentioning, our primary reference had looked at this equation, but not with this, if you like, this B field. Okay, so you can take this B field and set to 0, let's say. If you do that, then this first equation will be the Einstein's equation. Is that right? Yeah. So this first equation will be the Einstein's equation, which will remain. And right. So so in that equation, you can see that what is going to happen, you are going to have terms like this, okay, which has poles for certain values of omega. Okay. So this, violates that requirement that we had on the potential. Okay, naively speaking. So if you look at this equation, we'll say that, even if we look at this equation with B set to 0, we'll say, okay, well, my proof doesn't apply, like their proof will not apply. And you will say that, well, this thing may not work, but, if you go ahead and solve this equation, you find the QNMs and you find the 2-point function, then you will experimentally find out that the formula works. Okay, that they showed. Okay, but then they said that, look, the proof that we presented doesn't really work for this equation. Okay, because the potential doesn't satisfy the criterion of the proof. Okay, so good. So now, but now we have this complicated scenario, and this complicated scenario where this coupling is very hard to solve, both the QNMs as well as the 2-point function. Okay, that is very hard to solve. These equations are, in a coupled format is hard to solve. But this problem was simplified long time ago by a paper by Ishibashi and Kodama. Okay, what they did was they gave us a prescription to decouple these equations. Okay, so if you go into something called master variables, you can decouple these equations. Okay, and the master variables, this phi plus minus, okay, you see is related to the G and B in this format. Okay, as I have written. Okay, again, I'm sorry because it's a little complicated, but you see, I could fit it in one. It's not that bad also. Okay, so so this equation, this relation is slightly instructive. Okay, that's why I put it in. You see, so firstly, let me give you the punchline. What happens? So once I go into Ishibashi-Kodama variables, these master variables, and I try to rewrite the equation, you see, this equation falls in the same format as the scalar equation with a different potential. But now in this potential, there are no singular terms. It satisfies their criteria. So their proof applies to this equation, but written in Ishibashi-Kodama variables. That's our point. Okay, that's our observation. And why it is non-trivial to figure out if you are not looking at the charge, if you are not putting in the charge, that is not very non-trivial to figure out, because you see, the master variables are related to the G by a prime. you don't usually make that kind of substitution, right? In an equation, if you want to like even do some variable substitutions, this is a very non-trivial variable substitution, if you like. Okay, even if b is 0, this is a very non-trivial substitution that you can do in the equations, right? So, once you do that, then, even in that case, when b equal to 0, you will be able to recast the equation in this format. Okay, sir. In this format, where the original proof just applies, because it's again an equation which is Schrodinger equation with the potential, which has these nice properties, and then it applies. Okay. Yes.
The fields in different variables.
Just different variables. Okay, and those variables is also not our credit. That was there long time back. Okay, this decoupling of the equation, at least for the charged black brane. Okay, in this scenario, this is work of Ishibashi Kodama, where they did it in all like flat space, ADS, and for arbitrary lambda, they did it long time back. Okay.
You're trying to say that this Q being not equal to 0 is somehow important.
It's not important. That's what I'm saying. It's not important. It's not important. That's what I'm saying. So if Q is, even if Q equal to 0 and this B equal to 0,
Still everything works.
Still everything works, because you see there is, but seeing this may be very non-trivial. Looking at the equations, looking at these equations, with B set to 0, that variable transformation may be hard to find. But Ishibashi Kodama has a procedure that gives you this.
Once you get that, then you can go back.
But you see, once you get that, you know this. Okay. So what I'm trying to emphasize here is, here in this set of equations, you never had the requirement to go into more complicated variables. Okay. So this may not have occurred to the authors of this paper that, there is a complicated, variable transformation, after which, their own proof applies. Okay. That's what I'm trying to say. Okay. So, yeah.
And so, I mean, that is one. I plus minus is that f k square minus omega square.
Yes. Yes.
In the denominator.
Yes.
So the singularity is there already. Right?
So after absorbing the singularity, that's the
Phi plus minus has that omega square minus.
Right. When I write down the equation in the
I
phi.
understand. So this looks like a factorization.
Yes. So
But,
this thing
the
is absorbed in the.
problem of having a pole will remain, because eventually I have to solve for the phi.
Eventually, I have to solve for the value of omega. Okay, the QNNs. Okay, if I want to find the values of omega, that now I can do as you can see here, starting with this equation. Okay, so now what my problem reduces to. My problem reduces to. Yes.
Probably assume that this is a smooth solution.
Yes, precisely.
Then that violates the original expression that we speak in terms of omega square in space for A, because that can help you. So are you in the same class of solutions, or you are in a different class of solutions?
I am in the same class of solutions, because you see the solution is unique given the boundary conditions and given the boundary condition and given whatever variables I'm looking at. Okay, what are the values of omega for which I can solve the equation given this boundary condition? That's the question, right? Okay, so if I answer that question, I can try to answer the same question by differentiating the phi.
Go back and see that why.
No, but I think that
No.
if you want to know the boundary behavior, the boundary behavior is not due to the G and B. The correct variables should be phi on.
Let me try to say that more.
To understand how this translates back to the original problem.
As far as the omegas are concerned, they're identical. You can use that equation as well as this, modified variable equation. The values of omega don't change. Neither do the 2-point function. Okay. But now, the 2-point function here, if you calculate for the phi, that is not the same 2-point function for this, for this G and S. There is a relation. Okay, that you have to figure out.
There will be a singularity sitting there.
There can be a singularity sitting there, right?
It has to be.
Yeah. Because this is the statement. You take this equation and find the boundary behavior.
Translate to the statement of the.
So that G
So that is still valid, does it?
So
So
that
you see-
The class of solution we doesn't valid.
I mean, sorry, there.
Wait. So I am going to look at this equation, okay, which is the Ishibashi-Kodama equation, okay. And you see here, I have two different decoupled equations, okay. And I'm going to do the whole, I'm going to run the statement of the proof for this equation. And once I have done that, the QNM values are identical because the QNM values can never change. But now the 2-point function that I obtained from this equation, I have to relate to the 2-point function coming from the Gn, for the Gn. That I will do.
And that will translate to a statement W the potential.
So the potential is, this is the potential that I'm interested in now. Because, this is the equation for which I'm going to apply the proof.
No, I guess the point is that when you write the phi things, you'll have a G naught there because you can use the theorem. But when you translate it back to these variables,
There'll be a combination.
G naught might be a complicated function of omega.
Not only there's a complicated function, there'll be a combination. As you can see, the G naught for this, okay, there'll be two G naughts, right? Coming from here because there's a plus and a minus, right? And these two things will go and combine to give you the corresponding correlator for B and G.
One of the important things that you pointed out was that G naught was not a function of omega, right?
It is not a function of omega, it's a function, but it's a function of K, etc.
Yeah.
Right.
Is it obvious that when you translate it into these variables again,
Huh.
that it won't become a function of that?
Because
So let me say this. Here, there is a function of f and a z square here, right?
Yeah.
So if you look at the asymptotic behavior, okay, so you have to consider the asymptotic behavior of G and B, where you have to understand what goes in there. Okay, so I'll write down the relations where the asymptotic behavior of G and B is going to get related to the asymptotic behavior of phi plus and minus through this relation only that I wrote down. But for me now, the main equation is this decoupled equation. Okay, and the potential I should look at, because I want to apply the proof, is the potential of the decoupled equation. Okay.
That depends on what different function of the.
So I'm going to, from the decoupled equation, there are two things I'm going to calculate. One is the values of omega, the QNMs, okay, which are identical to the values of omega if I didn't decouple the equation. Okay, that's one information. The other information that I'm going to get out of this decoupled equation is the boundary 2-point function. Okay. The boundary 2-point function corresponding to this phi field, whatever that operator is.
If you are going to the boundary CFT,
Yes.
you will make comments about this phi,
The operator dual to the phi. There's some composite operator dual to the phi, right? And I'm going to make the comment about, correlation functions of that composite operator, whatever that is. Now I'm going to relate those correlation functions with the correlation functions of energy momentum tensor and the charge current.
So you only work in this composite operator.
I'm solving the problem in the composite operator language and then going back to the original, question.
Then in the original thing, somewhere this information would be there that there is this pole sitting there.
But this would go away if you
And
like.
This is an information that
Yeah. So see, there's a, so let me defer that question for a moment because I'll explain this better. But it is also a possibility that this pole vanishes if I take the boundary limit. Okay, it doesn't contribute in the boundary. It is also possible that it contributes. Let's keep us open, until I write down the expression. Okay, it is possible that this omega minus k behavior, this thing goes away if I take the boundary limit. It's not so. If I take this equation and consider the boundary fall off of phi and the boundary fall off of G and B, then it is possible that if I take the asymptotic limit, the contribution from this pole is just not there. Okay, it's possible, but it may be there also. Okay, let's keep open for that. But this is the what I'm trying to point out is that the new equation that I get, that can be again written in terms of a Schrodinger equation. There's a potential and the whole proof is valid again for the new equation. That's the basic point. Okay, so now if I take this and the first statement is that of QNMs. Okay.
It's a Fuchsian equation that is. So
Yeah.
Schrodinger equation doesn't have a derivative. So that's very different.
No, but it was a first derivative of a derivative again. There's a derivative inside, there's a prime inside. It's not a first derivative.
Yeah, but then the one term which comes with phi prime also. There's a by there.
Yeah, but if you go into, as you can see from this factor, if you go into this so-called, tortoise coordinates, then you can write this as del u square. This term converts into del u square. Yeah, so then you'll get a factor here, if you like. So then that is like a small modification to, yeah.
Slightly different.
As it is written, it's slightly different. I agree. Okay. So yeah, so you can, I wrote it, it's slightly simple to relate, but you can go to the, because, this is the format in which we find the QNMs and the 2-point function. Okay, with Z, it's simpler than with the tortoise coordinate, but
that connection.
Right. It's a flat connection equation. Yeah. Right. You can solve this equation given the boundary conditions, okay, numerically, because the potential is complicated. I didn't try hard enough, but I would doubt you can, okay, because the potential is not so easy. Yeah, essentially, so this is the thing. So you can take this equation, and what we did was we plugged it into this package, this QNM spectral written by Janssen, and you could get, modes. It's also very important. I could, so, it's important to get, so if you think about for a second that, our objective was to verify this formula, right? Which had products over infinite QNMs, right? So it's important to have information about all the QNMs to get any kind of match, okay? So of course, when you're doing it numerically, you cannot, have all the QNMs. You have to truncate somewhere. Now, what we do is, again, following the original paper by, Zivodev et al. What we do is, we truncate up to some value, okay, of QNM. Okay, as you can see, this, if you like, these QNMs, this like being referred to as the Christmas tree in our literature nowadays, that, there's this QNM spectrum of the year, where you see, there's a plus variable and a minus variable. Okay, these QNMs that we get are, one corresponds to, as I have marked with blue and red, they correspond to two different variables. Okay, so we'll get the same spectrum if we were to deal with the G and B initially, but we'll get different set of QNMs, if you like. We'll get all of them together. But in this case, we can get the blues separately and the reds separately. That's the point, right? And once we do that, then you see, we have to go up to a certain point in the QNMs, after which something very interesting happens. Okay, what happens is, after this, after a point, the spacing of the QNMs, that can be written in terms of some integer multiplied by some quantity. Okay, this kind of is a feature of almost all the spectrum that I had looked at, in particular the spectrum that I am analyzing here. Okay, that helps us enormously. It's an approximate thing. Numerically, it's an approximate. After a while, what happens? This feature is only an asymptotic feature, only for large omega, that the spacing between the QNMs, become integer spaced in a, like, integer times something. That kind of spacing, emerges, right? Now that we can say that instead of happening at infinity, is happening at 20. It's a good, within numerical errors, it's a good assumption. And once we have that, then the rest, if I plug in that formula, then the product formula, that translates into some kind of gamma functions. Okay, so you can incorporate that as a tail correction. Yeah.
Conditions that you say look like the conditions of gamma.
Yeah, it becomes
You have taken out this integer times whatever as a scale in the beginning, and write it as a gamma.
That's what we do. That's what the tail correction formula is. Okay, and that helps us in getting a very precise match between the two quantities. Okay, one is calculated through the omegas, where all omegas are present now. Okay, because I have corrected for this tail correction, and the tail correction means after 20, whatever exists, that is being incorporated into the formula, and then the 2-point function is also calculated. So 2 comments about that. So you see, I have 2 equations now. I just view their asymptotic follow-ups and just take the ratio as usual, as I did before. Okay, and thereby compute the 2-point functions like this. Okay, this 2-point function is for the operator dual to the master variable. Okay, this I'm not saying is directly related to the energy momentum tensor or J. That relation I have to find out. Okay, we'll talk about that relation soon. Okay, so this is what I mean by the 2-point function now. Okay, the retarded 2-point function, and I can convert it into the corresponding 2-sided Weightman, and I can find there are these 2 distinct contributions. There are off-axis poles and on-axis poles, and you can put them together, and you can see that there is a beautiful match.
So
Yes.
this 2-point function is a 2-point function in a CFT.
In a CFT of a operator which is composed of the energy momentum tensor and the current.
So from symmetry, is it possible to guess the form of, like, because in CFT you can use this symmetry.
But this is thermal CFT. That's the point.
Even if it is a thermal CFT, you can have this 2-point function, then fix that in terms of cross ratios. So from that code structure, can this be
The 2-point function, let's see. So yeah. So you're saying that you want to express this. So for the thermal CFTs, the 1-point function is non-trivial, right? So because the 1-point function is non-trivial, the 2-point function has, I would say, would have like this structure constants also, right? And then there'll be some dependence on the spatial part. And you are saying that, well, I'm not sure if that if that matching happens. I haven't checked that myself. But this is one of the things that I write down at the end of the, in my concluding slide. It would be interesting to cross-check the expectations coming out of, let's say, thermal 2-point functions and see how this behaves. Okay. Firstly, the omega dependence here is just, dependence on one time coordinate, if you like. Okay. And this is also, as we have constructed, this is like Lorentzian, right? And then,
it's not any thermal CFT.
yeah, it may not be generically provable. Okay, but with certain kinds of assumptions, but there's definitely a question of compatibility of this formula with what you expect out of, like writing down 2-point functions of, using, this CFT data, that is definitely there. Okay, I haven't cross-checked it myself. I don't think, these guys also do it. Okay, so, yeah, but here is the match. You see here, this continuous line is the continuous line that you get by putting it into the formula, because the formula is a function of omega, and there are, the values of omega n's that I have known from the plots. So you can get this continuous curve. Okay. And if you want to find the 2-point function by the ratio, asymptotic ratio, then you have to choose a value of omega and then find it numerically, right? That has been done on these, black dots. Okay. So as you can see, there's a very nice match, numerical match between the two. Of course, it had to be because there's a proof now, because the equation can be written in a way where these two things had to match. Okay. So that said, this comes to, so, this adds nothing to the paper, except that, we are looking at a different equation for which the match has happened. So this is entirely the expectation coming out of this reference paper that I was talking about, right? Now, the additional ingredient here is the following. Okay. Now we want to relate this 2-point function that I'm talking about in terms of the 2-point function corresponding to the currents. Okay. So the currents that are turned on in this sector, there are some, like 6 components of the currents in general. Okay. Which you can again throw away 3 of them and keep the 3 currents on. So that there are 3 sources, if you like, and you can differentiate the on-shell action with the help of these 3 sources, apply the ADS-CFT dictionary essentially. If you do that, then you will see that you will get the correlation function of the currents written in terms of the master variables through the equation where the master variable is expressed in terms of the metric and the gauge field. Okay, and that relation is of this form, that you see in general there are the 2-point function of any 2 current. This is the 2-point function coming out of the master variables. Okay. It is a linear combination of these 2, where these 2 numbers can be found by this asymptotic. We have the formula in our paper. We have worked it out thoroughly. That these 2, this zeta plus and zeta minus, these formulas we have. Okay. And if you like, that additional bit, which was there that we are talking about, that coefficient, can in principle go into this zeta plus and zeta minus. Okay. Because this relation is worked out from the asymptotic limit. Okay, of finding the on-shell action asymptotically and differentiating that with respect to the sources of the corresponding energy momentum tensor and charge currents. Okay, so this is the schematic form. Okay, and once you have that, then you know that my answer therefore of the 2-point function is the sum of 2 infinite products. Okay, where we have to emphasize this is like curly C. I'm sorry, it's not zeta. Okay, so this curly C plus and C minus I know. But what I don't know is this zeta plus and zeta minus. There's still an unknown that is there, okay, which is not fixed by QNMs, not fixed by my, asymptotic analysis. There's still one unknown that remains, which you have to fit by, you have to find by fitting the curves, of the 2 answers. Okay. No, that's the point. So omega dependence is entirely captured here. No. In general, this C plus and C minus can be functions of omega. Yeah. Okay. This in general can be function of omega. Okay. But the zeta plus and zeta minus is only function of K, which are these unknown, K or any other parameters, the Q and the background parameters essentially. Okay. So So therefore, this is the structure of the 2-point function. And yeah, I mean, if there is any relation like this, these relations can be exactly derived given the exact relation between master variables and yeah, and the asymptotic, basically the ADCFT dictionary, one can derive. So that is, yeah. Yes. No. Always there's two. There are zeros. That's very important. You see, this expression has zeros. This expression has non-trivial zeros. In fact, the referee asked, can you say something about the zeros? We tried to work these zeros out. I don't know, one of you may be a referee, in this room only. I'm not sure. But so they asked us, what is, so can you say, because we said nothing about the zeros. We said that the zeros will be there, but we said nothing. But then we introduced some analysis. We saw the zeros were occurring very close to, one can do some, very rough analysis. And we saw that the zeros are occurring very close, but not on the QNMs. Okay. So, there is a class of QNMs over which, very near to that, these zeros are occurring. Okay. Yeah, I mean, but we don't have anything, intuitive to say about these zeros. I'm sure they're very important. Okay. As you know, in this story, similar story, people have worked in complex omega and k, and this kind of zeros and the cancellation of the zeros between numerator and denominator plays important role in this kind of, this, discussion of chaos, etc. Right? So code skipping kind of thing, huh?
I was just going to say,
yeah.
In these original variables,
we could have had zeros. Yeah, that's why the proof didn't apply. Right. Exactly. Yeah. So the proof didn't apply to the original variable, but it applies to the master variable. That's the thing. Because I know the transformation, I know what it is. That's the point. Yeah. Very good. So this is the generic result. But now, so this is the thing about the thermal product formula. Okay. So most of the things that I had to say about it, I have already mentioned. But now I will just repeat this analysis for a slightly different system, a system which is very, if you like, dear to me for various reasons, which I don't want to get into because that's another story. So essentially, the bottom line is, ADS-CFT has always helped us to give us like a qualitative understanding of something that can be there, right? So, if you now take this U1 and make it an anomalous U1, which you can do by introducing a Chern-Simons term in the bulk corresponding to that U1. So essentially what happens, the boundary current is not conserved, but it is not conserved, in 4 dimensions, it is the current conservation is proportional to E dot B, if you like, in the corresponding boundary. But if there is no electric and magnetic field in the boundary, this is still conserved. Okay, it's a global anomaly. Okay, because there are no corresponding, electric and magnetic fields. So, and the proportionality constant is proportional to this value kappa here. Okay, that's the setup. Okay, so if you take this theory and if you can deduce certain things, qualitative, which are, where, this kappa is kind of responsible for a certain kind of physics, it often happens that physics is generally applicable to theories with, generic anomalies. Okay, this kind of things holography generally does. Okay, give us some generic ballpark qualitative understanding of things. Yes.
Anything, or is it quantized to some?
Very good question. Okay, so in this work we are assuming kappa to be anything. Okay, in this, we are going to vary kappa generally as a parameter. Okay, but in case of n equal to 4 Young mills, the value of kappa is fixed. I think it's some 4 by root 3 or something, root 3 by 4, something like that. Okay, here. So I think 4 by root 3. So that something like that. Okay, so this number is fixed. Essentially, you have a supersymmetric theory where you don't have a lot of leverage with all these parameters. So there is a value of kappa for which it is the correct truncation of n equal to 4 Young mills. But for the sake of understanding, we are going to keep kappa, like we can vary kappa, we can think of like varying kappa. So essentially, if this value of kappa depends on the species that you have in the boundary theory. Okay, so if you have, let's say, some wild fermions, like n species of them, then this kappa will be proportional to that, if you like. Okay, so yeah. So now let's take this system, and if we take this system, then you will see that this Maxwell's equation is going to get a correction from kappa. The Einstein's equation won't, because it's a topological term. So, there's no contribution to the stress tensor. And, but it so happens that if you have a electrically charged background, if you have an electrically charged background, which we have considered here, it so happens that only the shear sector, the sector that we have considered, gets contributions from this kappa. The fluctuation equations get contributions. Okay, so I can take the, so I have, this charged black hole was a solution to Einstein's equation with 0 kappa, and it is also a solution to this equation with non-zero kappa, because there is only electric field. And you see, this is 0 if you just have the electric field. Okay, now, so it is a solution to this system as well, but the fluctuation equations has the imprint of kappa, and it's only the so-called, shear sector which has the contribution of non-trivial kappa, the sector that we were looking at essentially. That's, the second motivation of looking just at the shear sector. Okay, so again, I will just repeat the analysis, but in this case, because of this, if you like, this effect of this epsilon, if you like, what happens is, this symmetry, I told you there are 6 kind of fluctuations. I'm not sure if I wrote that. Yeah, I wrote it down. There are 6 kind of fluctuations in this sector. Okay. And as I told you that, the 2 equations are identical for these 3 variables and these 3 variables. The 2 equations were identical if kappa was 0, but now they are not identical. Okay. There is a coupling between these 2 kind of fluctuations, the top line and the bottom line, by kappa. I think I have shown it here. Okay, so now you again go into the gauge invariant variables. After you go into the gauge invariant variable, if you write down the equation, you see there is a term involving 2, 1. If you write down the 1, 2 equation, equations, there are like 2 sets of such equations, if you like. And then there is there's the Maxwell equation only I wrote, there's a corresponding Einstein equation as well. But, the 2 sectors, these 2 sectors now, they are coupled with each other as well. Okay, so now, earlier I was talking about 2 sets of fluctuations. Okay, like, 2 sets of quasi-normal modes, but now I have 4 sets of quasi-normal modes, which I should, talk about. And one thing, so now I have to do Ishibashi-Kodama kind of variables in the presence of that kappa. So, there was a paper which does it, so we looked at the literature. There was a paper that I would say tried to do it. Okay, there's a paper by Matsuo and collaborators. And frankly speaking, what they said was, look, there is a coupled equation like this. So, you can write this equation as, a 4x4 matrix, multiplying the variables, and you go and diagonalize it, then you'll find the decoupled equation. That's what they say. Okay, so I think, we should take a little bit of credit in, doing that diagonalization and writing it in a form. This was a bit challenging. And, one of my students, Aditya, was like instrumental in diagonalizing this equation in the right form. And so he managed to write it in a form which can be easily plugged into the package, and, the QNMs can be obtained. The package was again important. I could write a code which will work well, let's say up to 10 QNMs. Okay, but I want the QNMs correct, very precise up to 20 QNMs order, like that. So the package was also important. So now you can take this, as you can see, there are 4 variables now. Okay, and you can take this, and there are plus minus 1, 2. There are 4 variables. So you can now repeat the steps, what I just discussed. And if you again, if you look at the effective master equations, then the potential has the right form which would be amiable to that proof. Okay, so here also you expect the same thing to hold. Okay, so and you could work out the QNM spectrum and the 2-point function. There are 4 plots now, as you can imagine. That also works out very well. And as you can imagine now, for the same current correlator, now instead of 2 terms, there are 4 terms. Okay, in the sum, because there are 4 sets of QNMs, so there are 4 terms. So you see, this problem of how many terms will be there in the sum is related to how many decoupled variables we have, how many non-trivial decoupled variables we have. Okay, so as soon as we, so let's say, I didn't know about this, but just I knew about the fact of decoupling. If I took the, took our, let's say undecoupled equation and found the QNM spectrum, if I could see that there are 2 branches of Christmas trees, I could take those 2 branches and construct the formula. Okay, so there's something generic happening here that, the decoupling, that happens would give you, 2 sets of QNMs essentially. Okay, so you could just look at the spectrum now, if you have this insight, and you could probably, write down this formula without the formal work. Okay, very good. So that was the basic point that and then, as you can see, there are very nice matches. If you now plot the, now here we have plotted this energy momentum tensor versus omega, like that you put everything
Just
together.
by looking at that, how many Christmas trees you have?
So let's look at this complicated one, most complicated one. You see, I agree that it is, you need very high precision. So, but here, so if you can figure out that there are 4 Christmas tree branches, okay, then you know that there are 4 terms like that.
No, that my question is,
Huh.
if you go to that,
Huh.
some
Huh.
sectors,
Huh.
I mean, you will not even know the CIs. Just
No, that just follows from, like the standard variation, that you can find separately. The CIs, you can just, do an asymptotic analysis of the equations and you can
So
find.
you're saying the fact that the thermal two-point function will be like this,
Huh.
the structure.
So there will be 4 numbers that you will not know. Given a value of k, there will be 4 numbers that you will not know that you have to find by fitting. Yeah. Okay. So good. So this does it. Now, while we were doing this exercise, so this kind of terminates my discussion, related to the thermal product formula. But while we were,
It will only be 4 numbers if you go to the right coordinates.
if you go to the right variables, if you like.
Basis, right?
Yeah.
Otherwise, there will be functions. As you say,
Yeah. So, right. I mean, so this is, this, so basically, so what kind of, if you want a, like an ansatz for a structure like this, so the ansatz, this is like a good ansatz. Okay. That's what I mean. Okay.
No, what I mean is, as you show, right? Otherwise, there will be like functions in omega on top, right?
So it is here also. So here this is sum, right?
The bottom, not on the top.
No, but there's a sum. There's a sum over 3 terms like this. It's a sum of product.
Yeah, that's fine. But
So if you put the bottom together,
There will be 4, I equal to 1 to 4.
that
You have to figure out from the.
that I stare that and I understand.
but what I'm saying is, you have 4 sum, let's say you had 2 terms like this, right? Then you combine the denominator, then you have zeros on top, right? The top function is not trivial, right? That's the point. Okay. So good. Now, while we are at it, 2 more points and, have I a long behind? Okay, fine. I'll finish quickly.
10 minutes.
And plus we had all of this trouble with plugging things.
Okay. See, this is supposed to, in my mind, I wanted it to get over in an hour, but anyway. So, yeah. So, yeah. Also, there were less questions. So, you promised me more questions. Yeah. Okay.
So I see. So you were playing mind with this question.
No, actually, okay.
So he was expecting more from us.
I was expecting more from you,
Sorry,
not
sorry,
us.
sorry,
Yeah.
I'll
Okay. So while we were at this, we noticed something very interesting. Which I found very interesting. Okay. So one thing is, and this may be of interest to people from condensed matter. So you see, what happens here, if we look at the evolution of these modes as a function of kappa. Okay. Now I'm saying this kappa parameter, this so-called anomaly parameter, this I'm keeping arbitrary. Okay. And I fix some large value of kappa, let's say, okay, some, here kappa equal to 1. Okay. So this value of kappa is not my n equal to 4 Yang-Mills value. Okay. It's, large compared to the n equal to 4 Yang-Mills value. Okay. So if I fix kappa to be 1 and, the background, charge density to be 1, if you like, then I observe something very fascinating. You see, as I increase the value of momentum, some of these top modes, go and close, go very near to the axis. And you see, when k is 1.5, it's very near to the axis. Okay. And it goes more and more near to the axis. So what happens is these QNMs kind of lose their imaginary part and they only have a real part left. Okay. As I increase the value of k. So these are some large momentum, like long-lived modes that emerges. And this effect is very, very particular to kappa because, we have also done the analysis for 0 kappa, right? So only for non-zero kappa, we see that there are these long-lived, modes that emerges, okay? And this effect is also very tied up with the anomaly coefficient. It's a kappa effect, okay? And this also we demonstrated by looking at the effective potential. Okay. So if you looked at the effective potential of the problem for which you had this long-lived modes, you didn't have long-lived modes for everyone. I think this is just phi minus, is it? I should have written it down. Yeah, minus. You know, one of the functions had this. Yes. It goes to the real axis. It hits the real axis. So this is omega axis. So this is like imaginary part of omega. And this is the real part of omega. It's a plot of that. The values of quasi-normal modes. This is the real part of omega, and this is the imaginary part of omega. And you know, if you, so this pink dot is one of the dots here, if you like. It's one of the dots here. Quasi-normal modes don't remain quasi-normal anymore. It becomes normal modes, you know, certain of them. Okay. And it's a, you know, it happens for relatively small values of K only. Okay. Like, you know, not, you know, you will not be find this in hydrodynamics for this because, you know, it's not happening at K near zero. Okay. This is a non-hydrodynamic effect. Okay. It has only, it happens at non-zero value of K and it goes, you know, and hits the axis. And this effect also happens particularly for a non-zero value of kappa. And then in the literature, I found there were several papers by Amos Yaram, actually, you know, who looked at a, you know, yes.
What happens to that value of kappa?
Value of kappa, it takes a very long time. You know, that's the thing. You know, that effect is, you know, so we can see the trend, but it doesn't really, you know, we cannot show a plot like this. You know, it just, huh? For anybody, for it takes very large value of momentum to, even if this effect is there, then the value of momentum is very large. Okay. So there are two effects that is leading to it. One is large momentum, as you can see, and the value of kappa. So if the kappa value is sufficiently high, it is basically quickening that process. You know, this scale that we are getting here is like controlled by kappa, if you like.
Go to kappa getting to infinity, can you push K to zero?
Yeah, okay.
These curves and asymptote to what values?
This is the zero line. This is the real axis.
Just.
So, and these are, you know, different plots.
But it goes over to infinity.
So you see, this point is already close to the zero line.
Yeah, that's the
so the imaginary part for this.
Part is zero, but for the real part, what's it going for?
Yeah, so it's a finite value of the real part. You know, it's like some 5 point whatever. You know, this is like whatever 6, 7. Yeah.
Does it go like this?
If you keep on increasing K, you know, this guy moves that direction. The trend is there. That's true. But this happens on the real axis.
Finite K.
Huh?
It doesn't cut the axis.
No, that's again a good point. Not in this case, in this discussion. Okay. These modes, that's a good point. Because if it cut the axis, then it would imply instability, right? Because it will have a positive mode, right? In this kind of scenario, it doesn't happen, you know, that instability is not there. Okay. It asymptotes, you know, it asymptotes to that line. But for all practical purposes, for as you can see, K equal to 1.5, it's very close to 0. Okay, so they are like seriously long-lived modes. Okay, and you can understand them very simply from this corresponding effective potential problem. The effective potential kind of develops a metastable, you know, minima essentially, which kind of goes more and more thick as you keep on increasing the value of K for a particular value of kappa. Okay, so essentially, if you think of that in some quantum mechanical terms, you know, these are modes corresponding to the ones that are trapped here, if you like.
So the anomaly is creating.
This effect is being created by the anomaly. This bump, you know, the significant bump at small values of kappa is created by the value of kappa. So if I make the same plot for kappa equal to 1.5 and K equal to 0, it will be a plot like this. We have it in the paper. I have. No, but because the potential depends on kappa, right? So it's a different potential in the presence of kappa. The effective potential in the master variables, it has a kappa dependence, right? I have it in the slides.
Right, but what does anomaly have to do?
This C has it. Yeah, this C plus minus has it.
I mean, in a sense,
I haven't written the C, unfortunately.
What does theory with an anomaly have to do with modes becoming long-lived?
Because you see, the anomaly is controlled by kappa. In 0 kappa, there is no anomaly. Okay. And it is this kappa that is controlling this long-lived modes, the presence of this long-lived modes. Therefore, I'm trying to insist or like conjecture, okay, so that you know, that these effects are related. Right.
Something like that. And that's it. But he's also saying that if it goes to the
Super Young's value that also.
Then it doesn't come back.
It doesn't, I cannot say it goes away. You see, at the super young man's value, what happens is,
So, but why are you thinking of last year's like the foundation? Okay, yeah.
see, as far as the Chance-Evans term is concerned, okay, so of course, this K is like the coefficient of the Chance-Evans term in the bulk, but this appears as the anomaly coefficient, if you consider the boundary, theory, okay. So this is the sense in which I'm calling kappa as the anomaly coefficient. It's proportional to that, okay. Of course, there are some factors, but it's proportional to that, okay. So, and if you play around with that a little bit, you find this effect, which is there. Okay, and so the statement is that if you look at a CFT or even a QFT where there is a global conserved current which is anomalous, then there may be a possibility of finding these long-lived modes in a thermal scenario, okay, which is a effect which is due to this, related to this anomaly coefficient. Okay, that's the possibility that this is. That can be generated, yeah.
Is there any value of kappa?
Huh.
Going to give this anomaly?
Huh. Will give me this anomaly.
Give you the anomaly.
Yes, correct. Any value of kappa. Yes. Yes, any value of kappa. That's right.
So why? It is for finite.
No, you see, let me explain that point once more. Okay. So what is happening is, you see, there's a value of K for which, it is tending towards this point, right? Note that this value of K is 1.5 here, right? So if I now change this to K equal to 2, let's say, okay, this, huh? No. So there are two players here. One is the momentum, which is K, and this kappa, which is my anomaly coefficient. Okay.
You're saying when kappa is changed to something else, this K will just shift.
The K value shifts. So if I increase kappa, K shifts down.
You have that trapping potential for smaller kappa.
The trapping potential, goes down, but, so again, the height of the trapping potential is a function of two things, kappa and K both. Okay. So if you sufficiently tune up K, then this trapping potential goes up. Okay. That's the point. Huh? So, if kappa is very small, for the n equal to 4 angles, the value is actually, as I said, it's, I think √3/4 or something like that. Okay. It's like very small. There may be pi's also. Yeah. That's the thing. At some value of K, which is controlled by kappa, you get this, long-lived modes. That's the point. Okay. I hope this statement is clear. Okay. So that's the thing, which I find this very interesting, because there could be effects related to this. That's one point. And the other point is what I think Urjunda was asking is, we also observe this point, this point can be seen from the effective potential. We also observe that, again, in the K kappa, parameter space, there are certain values for which there are modes, at least the on-axis modes, crosses the real axis. That implies instability, and that happens one by one. Like, I have shown two values. There are no modes above this. Okay, only two modes are unstable here. Okay, and this implies instability of a charged black hole. Okay, so this we felt was very serious.
This only happens when kappa is turned on.
Only happens when kappa is turned on. Okay, it's a kappa related effect. Okay, now we were like concerned that, okay, are we saying that for n equal to 4 Yang-Mills, if this effect is there somehow, okay, then, the charged black hole in n equal to 4 Yang-Mills is unstable. Is that what we're saying? Frankly, we couldn't settle this question to 100, but to our numerical approximation, we'll say that it's not. Let me explain this point a little bit, okay, in the parameter space. So this plot was meticulously made again by Aditya, very, he spent hours trying to plot points, finding these things were, not trivial, because you have to run the code for a while and then, collect these points, for various values. Then he put them together. So I'm showing you a schematic plot of the unstable region in K kappa space. Okay. There's a region in the K kappa space where you find this kind of dynamical instability of the system. Okay. And very interestingly, this line where, this kind of instability stops, this line is a function of the background charge Q also. Okay. And this line goes down as you approach the extremal black hole. So for the extremal black hole, okay, this region is the maximum region. Okay. So, So therefore I've drawn a schematic plot. Okay, for the extremal black hole, this region is a maximum. And what we find is, the value of kappa, which corresponds to this n equal to 4 value, for the extremal value black hole, sits directly on the, just below the point, where the instability starts. Okay. So, up to numerical accuracies, our claim is, this instability,
It's basically touching.
it's below it,
Allow.
it doesn't have the instability. That's what I mean. So, up to the numerical accuracy we have, n equal to 4 Yang-Mills will not, even the extremal black hole in n equal to 4 Yang-Mills will not have this instability related to this kappa. Okay. That's what we could say. But we had a very interesting way of corroborating this instability. Okay. This also we found, because once we saw this, we really wanted to understand what is going on. And then what one could do is do an extremal black hole analysis. Okay. So in the extremal case, what happens? The near horizon geometry develops a ADS2 kind of behavior in the extremal limit. And there you can go to near horizon coordinates and write down the corresponding equations. Okay. The master equations that we had, you could recast in the near horizon coordinates. Okay. Once you recast this in the near horizon coordinates, you see that this is this behaves like a massive scalar in ADS2. This equation reduces to the equation of a massive scalar in ADS2 with a value of mass which is determined by kappa and k, of course. As you can see, it's a complicated formula, but again, it can be included in a slide. And very interestingly, what happens, as somebody can already guess, for certain values of kappa and k, it violates the BF bound, of ADS2. So the instability is a near horizon instability that stems out. And it's a kappa effect. If you set kappa to 0, there is no such instability. You can check from this formula. Okay. And then also, so we have an analytic formula for that tip, because this is the analytic formula for that tip. Okay. And, from that analytic formula, we could say that again, n equal to 4 Yang-Mills value is slightly above, slightly below this point. Okay. So n equal to 4 Yang-Mills is, it could be also coincident. That's what, we feel. Okay.
So kappa deformed things are not. I mean, when kappa is not in the n equal to 4 Yang-Mills, it is not. Right?
It is unstable.
Yes.
Above that,
it's unstable.
Yeah. So above the n equal to 4 Yang-Mills value, for some value of k, it is unstable. It's a plot like this, right?
But just to go back to what you're saying, is this like a superconductor like instability happening?
No, it's not. I don't know. This is a big puzzle. I don't think, people I have spoken to, this is like a completely new kind of instability. I don't know what the end point of this instability is. It's not superconducting.
That's the ADS2, right?
Yeah, it's the ADS2, but I don't have a scalar field turned on in this game. It's an instability within the sector of Maxwell's Yang-Mills, Einstein-Maxwell.
I mean, maybe it's a scalar that you can construct out of the modes, which is becoming maybe not.
Well, as far as the truncation is concerned, it's supposed to be a well-defined truncation.
Yeah.
Okay. This truncation.
Always constructs scalar modes out of these, right?
Yeah, so that is the mode that I have written.
Yes.
This is a mode which is unstable, and it's a near horizon scalar mode.
And just think of that as your, as the sort of superconductor like thing in some sense.
Yeah, but then it will be like a superconductor involving a metric fluctuation.
Yes.
Which I haven't really heard of.
Effective in some sense.
Huh.
I mean, I'm just
Could be. This is like an exotic possibility. It could develop a metric here. That I haven't heard of. Okay. It will have it will be like a charge endpoint of this instability.
Yeah.
Could be a charged black hole with a metric here. I don't know if, I haven't really, I don't know about that. Okay. Also, it could be that, the black hole, starts moving or something, I don't know, like, shifting with some velocity. I don't know what the endpoint of this instability is going to be, right? So again, this is a very, I think, this is a very interesting thing. Again, it's related to the anomaly coefficient. Okay. So this, and this is applicable for our,
This instability is related to violating wave
violating the near horizon wave bound. So if you, if you go to the extremal limit, then you have a near horizon ADS2, and you can rewrite the near horizon equations in a way that it resembles the scalar equations in ADS2. And then you have an effective mass that you can read off. And that mass for a particular value of k and kappa violates the BF bound. That's the point. And that plot, starting from this formula is identical to this schematic plot that was obtained. Okay, this is the behavior.
So,
Okay.
so this instability, so that doesn't mean that it becomes instable in utility difference.
No, this is the dynamical instability of a black hole. So, if you do something to it, instability means, it leads you to another, solution, if you like. Okay. The instability can grow and, it leads to something else. Small perturbation, if you do, then the perturbation grows in time and makes it something else. Yes.
See extremely large limit, and you said you will ignore certain terms, and if you take those terms in account, then of course the structures will change. So why is it not conceivable that?
No, I don't understand. So we are always working in large N, if that's what you mean.
Yeah.
We are all, because this is gravity. So, we don't have to, in the gravity theory, you don't have, large N is automatic, So, if you're talking about, N equal to 4 Young-Mills, we are always working with large N, large lambda because we are doing gravity.
I see.
Okay.
So then one should take this instability seriously. That's what you're referring to.
Not for N equal to 4 Young-Mills, that's what my, but N equal to 4 Young-Mills sits at the border of the instability. That is my claim. It sits right at the border of the instability, okay, where the extremal black hole is, the extremal black hole has the largest region, and N equal to 4 Young-Mills value, sits right at this state. Okay, that's the claim. Okay, and it's kind of, like, if you like, approaching from below. Okay, I mean, frankly, we could not track this instability down starting with the N equal to 4 Young-Mills value. So you cannot really claim that there's the instability of N equal to 4 Young-Mills. Okay, that's the point. Okay. So, but yeah, if you increase the value of kappa a little bit, then you can see it very clearly. Okay, yes, I'm done, and it's very good time. So should I? Okay, this is my last slide. Okay, couple of comments. I'll terminate with my favorite ones here. There are many things I have written, and it's probably also some of this I've mentioned. So, of course, the endpoint of instability is something that I'm very curious about, because this is like a very standard, electrically charged black band. What can it, this instability is very, curious. Let me end with the last two, points, I will, because again, Neela is standing up. So let me so let me just end with the last 2 points, which I find is interesting. So if you look at these black holes, and so there has been a lot of work done for black hole, fluctuations of black holes, and if you like, holographic thermalization in the context of large D. Okay, so you just take the dimension of space-time and consider 1/d as a perturbation parameter. Okay, and you can look at these quasi-normal modes also. The equations become simpler, and you can in some cases even calculate the quasi-normal modes analytically also. Okay, in the large D limit. What happens there, very interestingly, is if you just look at the quasi-normal mode spectrum, there are 1 or 2 modes which dominates in large D, and all these other modes are suppressed in 1/d. Okay, so they are like 0. Okay, if you are in the strict large D limit, at leading order. So in that case, this implies that there's a very simple form of this formula in the large D limit, and maybe some kind of CFT expansion that is possible around this simple form of the formula. Then in the product there'll be just 1 or 2 terms, if that is true. Okay, if the large D limit, most of these modes are largely suppressed, then the leading order behavior will be given by just 1 or 2 terms. Okay, so if you now consider a CFT thermal correlator, one of the most complicated things, you may have a very simple form, and then you can develop a 1/d expansion in the in the CFT correlator itself. This kind of hints that such a thing may be possible. Okay, yes. So you can forget about kappa for this comment. You can forget about kappa for this comment. You can say kappa is 0, because you see N equal to 4 Young-Mills has SO6 R symmetry. There are some U1, there's only one U1 actually, which is anomalous, but the rest of the U1s are not. So both the system that we discussed are consistent truncation of N equal to 4 Young-Mills, kappa equal to 0 as well as kappa equal to 1 specific value. Okay, non-zero value. Okay, so this comment that I just mentioned, you can forget about kappa. Yes, you are right that in that case, large D, the chance of star will cause a problem. Okay, good. It's the dimension of space-time.
Ah,
Okay, so the idea is that, you just do a CFT, at some dimension of space-time, and then think of D as a, perturbing parameter. Okay, and then do 1 over D. Okay, like corrections. Maybe these colliators are simple there, and then, there are some corrections. This provides a kind of a hint that such a thing may be possible. Okay.
When you go to large D, why don't you approach mean field theories?
That may be possible. That it's a simple answer. Yeah, I haven't really thought about this problem from the CFT point of view. Okay, like, yeah.
Very large dimensions things simplify.
Simplify. Yeah, that is the statement that I'm making. Very large dimensions, this product formula will simplify and only have a couple of terms. That's the claim. Okay. Yeah. So yeah, that's some mean field thing. Maybe this is something that can be verified also, like, with holography. Okay. And the final comment that I want to mention is, this whole thing, you can ask, so let me, make just 2 comments and I'll stop. The first comment is this proof that these guys reproduced is not in the main text of their paper, the primary reference that I talk about. The proof is in an appendix for a very interesting reason. They copy the proof from a quantum mechanics book. Okay. And sorry. They copy the proof from a quantum mechanics book because this is a quantum mechanical problem where scattering amplitudes are essentially given by bound states, okay, in a specific way.
So
And yeah, there's a reference in the paper. I just forgot. In one of the, not that's not the book that I read, but yeah. Certainly not Sakurai. Yeah. So that reference is not Sakurai, but Sakurai might have it. Yeah. So no, but Sakurai writes down these formulas, but it doesn't comment in what is there in the numerator. That has this involved proof, right? But the point is, of course, these are poles. The bound states are poles of the scattering matrix, right? But then, the poles are everything. That's the statement. Okay, and that appeared in a quantum mechanics book, which they reproduce in this appendix. The kind of thing that I discussed initially. So so now you can ask that, is it possible that for a flat space black hole also, such a thing is applicable? You have a fluctuation equation, and then, the thing for 2-point function for flat space black hole is something called gray body factors, something people worried about pre-ADS-CFT a lot. Okay. And maybe even now people do, in the gravitation community. Okay. So, it could be that if you just find the analogy, then it could be that there is a relation, non-trivial relation between gray body factors and QNMs, which are like kind of exact in this sense. Okay. I tried to do a literature dig, and apparently there are some papers which tries to claim that. Okay. But I found them very hard to, like, what they say is, like from 2 QNMs, they're producing the whole thing or something like that. Okay. I didn't find the papers very convincing, but it seems that there is some people in the community who have independently tried to look at a similar problem in flat space. Okay, and then maybe some avenues to, work there. Let me end with that. Thank you very much.
Well, maybe one quick question, and then we can continue over discussion, but just to end the session formally. There were a lot of questions, but well, from this one,
Yeah.
So the plot where you showed that there's QNM asymptotes to the daily level. So how quickly is going to asymptote?
That depends on the value of K. How quickly, so, this asymptotic behavior is happening as I crank up the value of K, that is spatial momentum, right? And how quickly it will go is controlled by kappa. Yes. So if I turn up kappa, then it happens faster.
So that's what I'm understand. Like if I turn up in such a way that it asymptotes faster, then I will have a long limb which have a
Smaller value of momentum.
So that should basically for hydrodynamic momentum.
No, but hydrodynamics is really an expansion about K tends to 0. So what you are saying, maybe at infinite kappa, there is some hydrodynamics behavior that appears. I don't know, I'm just saying. But as long as kappa is large but finite, this is going to happen at a finite value of K. Okay. But hydrodynamics is literally, 0 value of K expanded. Okay. So any finite value of K is very far away from hydrodynamics, if you like, which is an expansion about 0 omega and 0. Okay. But again, I must say that if you take into account sufficient derivatives in hydrodynamics, Okay, like
Yeah.
high derivatives,
High derivative.
may be possible, I don't know.
Hybrid.
Yeah. Yeah, because there are, the transport coefficients at higher and higher orders, they have kappa in there, okay? So, it's not very clear to me that, if you go to subject high orders, second order, third order, that this cannot be captured for large enough value of kappa, that is not clear. Okay, let me say. But yeah.
Okay, maybe, we will end this session formally and